All right, we're on the third section in geometry, chapter 3, and now we're going to show you how to construct a perpendicular line to a line through a given point. So we're not doing the perpendicular bisector. I just want to know how to construct a line through P that's going to be perpendicular to M, line M. All right, I have to turn the paper around so the point is at the bottom. I don't know why. You might not have to do that, but I do. All right, so you're going to put the pointy part on the point that you want to go through. You want your compass open far enough so that when you swing an arc, you're going to intersect the line that you want to go to in two distinct places like that. All right. Now you're going to, you want your compass point. Now you want it more than halfway between these two sections. And then you're just going to swing an arc above that line from both points so that you get that intersecting mark right there. And I'm just going to connect this intersection to my point P. I'll turn it right side up so you can see what's going on. So from there to there. And that is at a 90-degree angle through this point to this line. Okay, you're going to need to know these, how to do this one, because you're going to be finding altitudes of a triangle. The altitude of a triangle is the line segment that connects a vertex to the opposite side at a right angle. Okay, so if you look at the construction that we just did, this is the line that we go to, this is the line, and this would be like point P. This is the point that we had to go through. Okay, and this will lead us to conjecture C7. It's called the shortest distance conjecture. The shortest distance from a point to a line is measured along the perpendicular segment from the point to the line. And you guys can see, you've heard that before, the shortest distance between 2 points is a straight line, right? Well, what it means is a straight line that's perpendicular. And you can see that that's probably true. I'm going to go ahead and just jump right into the next section because it doesn't take very long. And this is constructing angle bisectors. So I want to know what line, it's obviously going to be inside the angle, that will cut this angle exactly in half. All right. And again, I'm going to turn the paper just because it's easier for me if the vertex is pointing down towards me. Okay, so you're going to put the pointy part of your compass on the vertex, and you're just going to swing an arc. It doesn't matter. Doesn't matter what the opening is of your compass, but you want to intersect both sides of that angle like that. And now you're going to put your compass point on one of those intersection points, and you want your compass open to more than halfway the distance to that other intersection right here. And then you're just going to swing an arc on the inside of the angle from each of those marks that you just made. And look, you have intersecting arcs. You know you got to connect that intersection with something, right? You're going to connect this to the vertex. And that is the angle bisector. Pretty slick, huh? And this leads us to C8, which is the angle bisector conjecture. If a point is anywhere on the angle bisector, then it's equidistant to the sides of the angle. Well, let's look at what that means. So if I have a point right here, I know that the perpendicular to that point and the perpendicular to that point are going to be the same. Any point along here is equidistant to both the sides of the angle. And then that also leads us to the angle bisector concurrency conjecture. That might be a new word for you. The three angle bisectors of a triangle are concurrent. In other words, they will all three meet at the same point. So for instance, if I bisect that angle, and I bisect that angle, and I bisect that angle, they're all going to meet at the same point. That's it for 3.3 and 3.4.